All right, this is Mr. Zondo here again. Today we're going to do some 8-3. One more fun fact about me is my favorite color is green. I have my nice green cup right here. Fill with some water in case I need to take a drink. But 8-3 is going to talk about quadratic functions in standard form. So last time you did 8-2, which was going to be vertex form. So this is another new form for quadratics. Just like with linear equations, we had 3 different forms. We had the y equals mx plus b for slope-intercept. We also had point-slope form. We also had standard form. We're going to realize that quadratics also are going to have 3 different forms, and this is form number 2. This is going to be a quadratic function in standard form. So that's what we're going to learn about. We're going to learn about how it's different from vertex form. We're also going to graph using standard form, and the lesson vocab is only going to be standard form. So the other thing that you might need is you might need your notes. Other than that, we're going to give it a go. So starts out again with the explore and reason section. So we're given these 3 different graphs. So we're given g of x, we're given h of x, and we're given j of x. So at first ask just what do they have in common? How are they different? Well, they're all parabolas. So they all have that U shape. They all cross at 0, 0. So they all have the same y-intercept. But they're kind of different. Looks like they might be different shrinks. Maybe not. Nah, because they all start with 2. So they're all the same shrink. Whatever is going on here, it puts them in different locations. So that's why they're different. They're not all in the same place. You can see their vertex, all the vertices are not in the same places. So if we check out just the x-intercepts for the red one, for g of x, we've got one at 0, one at 2. For the blue one, one's at 0, one's at 4. And for the green one, one's at 0, one's at 6. Okay. So it seems like these numbers are all giving us the other x-intercept that's other than 0. With the y-intercepts, they're all 0, 0. That kind of makes sense. If we plug 0 in to any of these equations, we should get 0 back. The final part's kind of the weird part. It says we're supposed to look for a relationship. So it says look at the ratio b divided by a and compare it to its graph. So up here they say we've got graphs of ax squared plus bx. So if I do the red one, b divided by a is going to be negative 2 divided by 2, which is negative 1. If I do the second graph, negative 4 divided by 2 is negative 2. And if I do the last graph, let's do that up here, negative 6 divided by 2 is negative 3. So those all go up by 1. We also want to look at this, how it compares to the graph. So if I look at where negative 1 would be important on this graph, well, we'd have this part, but nothing's over here. So it seems like there's nothing that's really going on with negative 1, because the red one doesn't go all the way down here. But if we look at the vertex is at 1. We look at the vertex of the next one, 1, 2. Vertex, the x-coordinate's at 2. We look at the green one, the vertex, x-coordinate's at 3. So even though we get the different signs, which kind of throws things off a little bit, we still get the different x-coordinates of the vertex. Now the reason we know this isn't going to throw us off too much is because when we did vertex form, remember when we had the x-coordinates, it was always the opposite. So we would expect it to be at x equals 1, x equals 2, and x equals 3. So that's kind of cool that happens. That might not happen all the time, but it does happen for these ones, which is kind of cool. That's nice. So we're going to look at example 1. Example 1 just asks us to look at standard form itself and focus on the c value. So what information does c provide about the graph of f of x equals ax squared plus bx plus c? Well, just like when we did y equals mx plus b, we had the number on the end, the b value. In this case, the c value is going to be the y-intercept. So that's going to be what c is. It's going to tell us the y-intercept. It's also going to be, remember, if we were doing functions, that would be the initial y value, or the initial function value. So when we did a whole bunch of problems that dealt with money, where you had to put money into maybe a, well, that would be the exponentials, but if you had a certain amount of money on the gift card and then it went down by so much after you spent it, the initial value is always what we started with. it was the B value. In this case, since we've got 3 letters, it's going to be the C value. It's still the one that doesn't have a variable on it. That's what C is. Down here in the try it, then it kind of relates it again to some of the function notation. How does f of 0 relate to our result for example 1? Well, if we find f of 0, remember that means we have to plug 0 in for each of the x's. This one over here too. So we get a times 0 squared plus b times 0 plus c. Well, anything times 0 is still 0. So this is 0. B times 0 is 0. C is just C. 0 plus 0 plus C is C. So it does turn out with our function notation that C is the initial value. So C is f of 0. So C is what we start with. So that gives us a little hint as to what C is going to do, and it also gives us a little preview of standard form, because the next slide tells us about what the actual equation is, and this is the notes part. So Pearson has a nice example, a nice definition for standard form. It tells us standard form is f of x equals ax squared plus bx plus c. So that's what standard form is. So this is our standard form. Now it does tell us that a can't be 0, because if a was 0, if we got rid of this, we would just end up with bx plus c, and that would just be a line that looks like mx plus b, just with different letters. Instead of m and b, it's got b and c. So if we got rid of those, we would end up with just a line. We just have a linear graph. So that's why we have to have a not be 0. It tells us again, c is the y-intercept of the graph. We kind of learned that from example 1. The axis of symmetry is the line x equals negative b over 2a. So that's, if you're taking notes, that's going to be an important one, because that's not one that's really intuitive yet. So we just want that to be one of the formulas, and that's going to be the x coordinate of the vertex. So that'll tell us where the x coordinate of the vertex is, which we kind of looked at in the explore and reason section at the beginning. So this will give us the x coordinate of the vertex, and it also gives us the axis of symmetry. So this is also going to be the axis of symmetry, which remember, oops. So the axis of symmetry, if we remember the AOS, that's where we could fold our parabola around itself. That was where we had our symmetry. So those are our big points for standard form. So that's what kind of makes it a little bit unique compared to vertex form, which you had last section. So this is what makes this one nice and useful. So if we move on, so if we look at example 2, we want to graph this. We're going to graph 2x squared plus 4x plus 3. Find the axis of symmetry, vertex, and the y-intercept. Well, first things first, the easiest thing to find is the y-intercept, because the y-intercept is always just the c value. So the y-intercept is 3. So I can just graph the y-intercept as 3. To get the axis of symmetry, so remember, to get the AOS, we had to use that equation. X equals negative b over 2a. Well, if I look here, this is b. B is 4. So negative 4. 2a. Well, a is 2. So 2 times 2. So negative 4 over 4, or negative 1. So I know that's where my axis of symmetry is. So I need a nice dashed line at negative 1. All right, that's a really big dashed line. Let's see if we can change the settings on that. Make it a little bit thinner. So too thin. That looks pretty good. Let's move it a little bit. Perfect. And one last thing. Can I make it red? I can make it red. There we go. So now it all fits in. So that's my axis of symmetry. I want to state that very specifically what my axis of symmetry is, because again, there will be some questions that just tell you, hey, give me the axis of symmetry. So the axis of symmetry is x equals -1. Remember, we want a whole equation for the axis of symmetry. We don't just want a point. Last thing we want to get is going to be the vertex. So to get the vertex, we need to plug -1 into the equation. Plus 4 times -1 plus 3. And we'll just do, again, we'll quickly do it. -1 squared is 1. 1 times 2 is 2. 4 times -1 is -4. 3 is 3. 2 plus 3 is 5. Minus 4 is 1. So my vertex is going to be at -1, since that was my input. 1, since that was the output. So we'll come down here to -1, 1. And we'll make our point. Now we know if we want to make 3 points, if we want to make a parabola, we do need 3 points. But since we're symmetric, we can take this point and just reflect it. I want to do that in red since we're using the line of symmetry. Just reflect it. It's because we're 1 to the right. We also have to be 1 to the left. Now comes the challenge. We have to draw a nice U shape here. Let's see how well we can draw a U shape. And that looks okay. Hopefully your parabola looks a little bit nicer than mine. The one part kind of looks a little bit weird. That part looks a little bit funky, but otherwise, pretty decent parabola. So if you wanted to graph it by hand, you can. That's how you would graph it by hand. Then there's a couple try-its. So, like I said, if you wanted to graph it by hand, feel free to keep graphing them by hand. We do have graphing calculators at our disposal, so if we wanted to, we could just bring up Desmos. So we're going to go ahead and graph the first one. X squared plus 2x plus 4. We can get those same 2 key points that we had before. So we know the vertex is -1, 3. So let's go ahead and write down the vertex. So vertex was blue, so vertex we found was at -1, 3, because that's the top or the bottom of the parabola. Desmos made that really easy. I didn't have to do any of the calculations. The axis of symmetry, we said that one was going to be red, so the axis of symmetry is x equals, well, it's whatever the x coordinate is here. X equals -1 is the axis of symmetry. So we did that. We did the vertex first. And so the last thing we need is the y-intercept. Well, I could go back to my graph and look it up, but I always know it's right there. This one's easier to do without the graph. Let's not put it equals. So my y-intercept is 4. That was easy to do without the graph. If I want, I could click on Desmos also and see, oh yeah, there it is, right there, 0, 4. But I don't need to. For the second try, basically the same thing. Now my parabola is all the way down there. I get my vertex to -1. I know from that my axis of symmetry is the x-coordinate of the vertex. So x equals 2. Again, remember, you have to make that one x equals because it is a line. It's not just a point or a number. And then again, I didn't look it up on the graph because I knew it's right there, but the y-intercept is -4 this time. So we always have to keep the sign. If I did want to check it out, oh, look, there it is, 0, -4. So you can do it by hand or you can do it using Desmos. It's your option. So you get the choice as long as you've got that. You can also do it in the TI calculator. That would also work as well. To do that, you hit the second calc, and then you go down, you pick maximum or minimum, depending on what you got. So for example 3, we're going to check out this fountain. It tells us the trajectory of water from fountain A is represented by the function, while fountain B is represented by the table. There's a picture of our fountains. Compare the vertex of each function. Which trajectory reaches a greater height in feet? So if we look at the picture, they look about the same. I can't tell. So I can't use the picture to answer it. So I'm going to go to fountain A, and I've got to find the greatest height. Well, the greatest height has to be the vertex, because the vertex is either the maximum or the minimum. we can tell we're opening down, so it's going to be the maximum. So again, I can do this by hand, or I can just throw it into the calculator. I may as well throw it into the calculator because that's why we have the graphing calculator. So we're going to bring up example 3. There's going to be my fountain. Ooh, it goes really, really tall. So let's go up and let's find our vertex. Our vertex is at 1, 9. So we have to remember, since we want the maximum height, we only need the 9. We don't really need the 1 in this problem because we're just looking for the maximum height. So the maximum was at 9. So our job is to find out if fountain B ever gets up to 9. Well, it looks, since we said that everything was symmetric, since it looks like we got the same numbers on both sides of 10, this looks like it's my axis of symmetry. Since that's my axis of symmetry, that's where the vertex is. Since that's where the vertex is, that's how we know that the max here is 10. So which one is greater? Well, fountain B is greater because it's 10 versus 9. So in our picture, B should actually be at a greater height. So maybe we've got a perspective thing. Maybe A is just closer to us in the foreground, B is in the background. That's why it looks like it's the same. But according to our table and our equation, our function, B is going to have a greater trajectory, 9 feet versus 10 feet. All right, for the try it, it's pretty much the same thing, except this time they gave us the graph, so we have to again find out which one has the greater maximum value. Well, here, since we are given the graph, we can tell the maximum value is at 0. That doesn't seem like it's very big, but the other one could have a negative maximum, and then we would have to pick this one. So we're going to graph it, and we're going to find out. So we're going to say goodbye to this one, and we're going to bring up example 3's try it. We can graph it. It's kind of down there, but it does look like it's above the x-axis. It's at negative 1.1. That's it, just 0.1. Okay, well, for this one, 0.1. So which one has the greater maximum value? Well, we have to compare 0.1 to 0. 0.1 is just a little bit bigger. So we would say f of x has the greater max. Because again, we just have to look at our vertex because the vertices will always tell us either the maximum or the minimum. And since we can tell it's opening down because of the negative sign, we know it's a maximum. All right, moving on to example 4. For example 4, Mia is going to toss the ball to her dog. Can't see that distance down there. We're given a function for her ball. It's negative 0.05 times the quantity x minus 2 squared plus 8, and that function represents the ball's path. So first, before we're asked to do anything, it says, what does vertex form tell you about the situation? So this is kind of like we have to remember from the last unit. So last section said, all right, well, vertex form told us where the maximum or the minimum was. So it's going to tell us where the max is. And vertex form will actually give us the numbers. So we know we have to flip this one because we're inside the parentheses. So the max is going to be at 2, comma, and over here is going to be the y value for the maximum, 2, comma, 8. And yeah, it looks like in the picture, the top of the ball's path is at 2, and 8 is up here. So that's looks like it's a couple feet higher than Mia is. Mia looks like she's 6 feet tall. So that's what vertex form tells us. Now, what does standard form tell us? Well, that's what we did this section. So standard form is going to tell us the start. It's going to tell us the initial y value. I want to do this in purple. Like that, like that, like that, and like that. So we're going to get our initial y value from standard form. Now, we don't have standard form. We're only given vertex form. So that means that if I want to use standard form, I need to go ahead and put my equation into standard form. U up there. So we're going to do that. We're going to transform our vertex form into standard form. So the first thing we want to do is we want to take care of our order of operations. Order of operations always says we got to do exponents first. Well, parentheses first, but we can't subtract x and 2. So for PEMDAS, we got to do exponents. So our exponent says I have to do x minus 2 squared. So we actually have to multiply out our two binomials. And again, you can multiply those out however you wish. I'm going to go ahead and multiply them out with the boxes. So we've got an x minus 2 times another x minus 2. So we get x squared minus 2x. X times minus 2 is minus 2x. Negative 2 times negative 2 is positive 4. But again, you can multiply that however you want. If you wanted to do FOIL with the distributive property, you can do that. If you memorized it, because it's a special special multiple, you can also memorize it that way. But then at this point, what we need to do is we need to take our we need to not take our GCF. We need to combine our like terms. So x squared minus 4x plus 4. Now the problem is we still have the whole rest of the problem. So everything else that's in the problem is still around. So this is in parentheses. We still have negative 0.5. We still have plus 8. But all we did is we turned this x minus 2 squared part into the x squared minus 4x plus 4. All right, so from here, now we get to distribute. So we're going to distribute this negative 0.5. So we're going to get negative 0.5x squared plus 2x minus 2. And then in black, we still have plus 8 because I didn't do anything with the plus 8 yet. All right, almost there. We got one last thing that we got to do, and that is combine our like terms again. So we have one more set of like terms. So our final result, negative 0.5x squared plus 2x. And now we're going to combine those. Negative 2 plus 8 is plus 6. Wait a second. What did we say 6 was earlier in the problem? I seem to remember something was 6 before. Well, 6 was about how tall Mia was. So 6 is the initial y value. So we found out that we're going to start at 6. So we're going to find out that Mia is going to throw the ball right here at 6. Well, I guess we could have figured that out by the picture, but we did the whole equation just to kind of run it out so we could see that we can transform vertex form into standard form whenever we want. To do that, all we have to do is multiply the binomial and then combine a bunch of like terms. It's not too bad of a process. And that's it. That's all we'd have to do. So that tells us what vertex form tells us. We found out what standard form tells us. So that's the difference. So we can see they each have their benefits. Vertex form is good at telling us the maximum and the min. Standard form is good at telling us where we start. All right. For the try it down here, we're given another equation. We have to find the ball's initial and maximum heights. Well, the maximum height, we may as well just grab the vertex right away. So the maximum height is going to be the y value of the vertex. To get the initial height, again, just like the last example, we got an option. We can either run through all the math and do all the algebra like we just did, or we could just throw it in a Desmos or a TI graphing calculator, which is what I'm going to do. So over here, we got example 4. Plop it in. We see, yep, 6.25 is in fact the maximum. And we see our initial is 6 again. So that's it. We can just say that the initial is 6. There we go. So the initial height is 6. So I mean, maybe Mia is just throwing the ball again, but she just throws it at a different angle. So that's what gives us a different equation. But we get 6 again, so maybe it's Mia again, maybe it's somebody else. We're not quite sure. But that's how you can do it using either Desmos or you can do it using the algebra. So we did the algebra up here. You can do it using Desmos. You can just read it off the graph. And that's the last example for this section. So in summary, again, they tell us that today we did standard form. So ax squared plus bx plus c. A is not 0. C is going to be the y-intercept. We have this equation to get the x-axis of symmetry, or the x-coordinate of the vertex. To get the y-coordinate of the vertex, they have f of negative b over 2a. We simplified that to just plug it in. Whatever you get here for the x, you plug it into the equation, it gives you the y, or the f of x. And then they have it down here with numbers, so they replaced all of the algebra letters with some numbers, so you can follow it along there and see, yeah, okay, it works out with the numbers too. So that's everything for 8.3. Have a good rest of the day.